So this is our last lesson on matrices, and I just wanted to do an example of using matrix algebra. And the example is going to be deriving the formula for regression coefficients, the OLS formula for the betas that tell us the effect of each independent variable, the estimated effect of each independent variable on our dependent variable. Okay, so just reminding ourselves what the regression model looks like, y equals x beta plus epsilon, and also reminding ourselves that y is an n by 1 vector of observations on our dependent variables. That's a vector of numbers. X is n by k. It's, again, it has n rows, 1 row for each observation, and it has k columns, 1 for each independent variable. And we are estimating a beta for each of our independent variables. Each of those betas is going to tell us, does that independent variable affect the dependent variable? And if so, is the effect positive or negative? And then we've also got to think about the fact that there are these error terms that we don't observe. There's one associated with each observation, and that's the part of the dependent variable that we can't predict with the independent variables. Okay, so with that set up, let's first do a counterfactual. To set up the problem that I want to solve, let's imagine a world without any kind of random errors. Okay, imagine a world where we could perfectly predict the dependent variable using those independent variables. That never happens in social science. Forget about that. Our theories do not have that kind of precision. But let's think about what it would be like to be in this world. Sometimes that world's called a perfect fit, in the sense that our model perfectly fits the data. So we don't have those epsilons, we just have y equals x beta. And if that was the case, and since we're like imagining things that we wish were true, also imagine that x inverse exists. And then all we have to do is pre-multiply both sides of this matrix equation by x inverse. Let's do that. So x inverse y equals x inverse times x beta. Okay, well, x inverse times x, that's the identity matrix times beta, and that is beta, and we've found those parameters that we were wanting to find. Okay, we found we could find this inverse matrix of x, and if we have data so that all the rows and columns of x are filled with numbers, there's also going to be a matrix with numbers in it, and this is going to be a vector with numbers, and we do the matrix multiplication, and we'd have our betas. Okay, so you might be thinking, well, that only works if x is square, and you're right. If we had a perfect fit, all we would need would be as many observations as we had parameters to estimate. We just need, if we were trying to estimate beta 0, beta 1, and beta 2, we would just need 3 observations on x. And so x would be a 3 by 3 matrix, and we could invert it. That's not the world we live in, right? We always have omitted variables. We have often noisy measures of the things that we're thinking of. There's all sorts of things that make social science data have random components. So when we're in that world where every observation that we have has something that's making it a little bit off, something that's making it deviate from our theory, then we want as many observations as possible to get at the part of each dependent variable that is predicted by the independent variables. Okay, so in the real world, let's go now to reality. We have error. We want to have more observations than we are estimating parameters. Okay, and ideally we want to have a lot more. Okay, so x is not square. But check this out. X prime X is a matrix multiplied by its transpose is always going to be square. And let's just check that. So X is n by k. So X prime, X transpose is k by n. That's always going to be square. All right, so let's think about that. And let's continue to think about, like, so maybe that's invertible too. Maybe X prime X inverse exists. Let's think about that. And let's go back to our original regression equation, the one that had the error term in it. Okay, so we have y equals x beta plus epsilon. Okay, so here's my algebra. Just watch this. First thing I'm going to do is I'm going to pre-multiply both sides of the equation by x prime. And I'm going to do this. X prime y equals x prime x beta plus x prime epsilon. Is that all conformable? Let's check. So x prime, remember x is n by k, so x prime is k by n, and y is n by 1. Okay, so that checks. X prime is k by n, x is n by k, beta is k by 1. So x prime x gives me k by k. Multiplying it by beta gives me a result here that is all conformable, and the result here would be k by 1. This also would give a k by 1 result. And once again, x prime, k by n, epsilon, n by 1. We're going to get k by 1 here. So good, the conformability all looks good. Step 1. Next step, let's assume that this x prime x inverse exists and multiply both sides by it. Again, so I'm going to pre-multiply both sides by x prime x inverse because I'm conjecturing that it exists. And now it's not sounding so crazy. Like with x, no, x is typically not square. The inverse is going to exist. X prime x will be square. And it's not crazy to think that the inverse exists. So now we have, let's get back to the colors that I like here. X prime x inverse x prime y equals x prime x inverse times x prime x beta plus x prime x inverse x prime epsilon. All right. Oh, look how cool this is. Right here, I have something pre-multiplied by its inverse. Okay, so yes, it's itself a product, but here I have x prime x and x prime x inverse, so that equals the identity matrix. And so just recopying here, x prime x inverse. Remember, we're reverting the whole thing here. We can't invert the components because neither x prime nor x are square, but we can invert their product. So x prime x inverse times x prime y equals beta plus the same x prime x inverse x prime epsilon. Okay. And the last step that I'm going to kind of wave my hands over, but let's step back and think about what we have here. We have numbers for the x's, so x prime x, x prime x inverse, all those things we can calculate, and we've got y's too, so we can put numbers on all of that. We don't have numbers for the epsilon, okay? The epsilons by definition are the things that we can't observe, so that's what's not going to be part of our estimate. And when we put the hat on the beta, so to speak, okay, so putting the hat on the beta changes it from being the true beta that we can only theorize about to the estimate based on observable data. And this is indeed the formula for the the regression coefficients, x prime x inverse, x prime y. That's how the regression coefficients that R or Stata or whatever you use spits out for your data set that tells you whether your hypotheses are supported or not with the data. Okay, so just a preview of some of the things you're going to learn in 200B, and the last thing that you will do in our matrix algebra unit here is workshop 9, where you'll go through this process of finding the estimates for beta hat, the x prime x inverse, x prime y values for a little fake data set. So have fun with that.